Our topic for today is comparison of series. Let me start with the disclaimer. You can use this methodology only for series with positive members, not negative actually. So only for series with non-negative members. So let me state the theorem. No, it is 9.12. And this one is called direct comparison test. So let me state first. So let 0 be less or equal n less or equal to bn for all. Actually, it's enough after a while as a convergence. Then number 1, if sum of bn and goes 1 to infinity converges, then sum of a and when it goes 1 to infinity also converges. If sum of a and n goes 1 to infinity diverges, then sum of bn also diverges. This is just common sense reasoning, but there is also one very important warning about the way how you apply it. So generally, you see, first we said this is only for series with non-negative members, and that's emphasized here. So I told you that metaphor that for a series with non-negative members you are adding positive mass. So the only question is, so that mass is getting bigger and bigger cumulatively. So the question is, will it stay under control or it will just go to infinity? So generally what? Drops for Bn are bigger than drops for An. So what? If Bn stays under control below a certain bound, then An adding smaller drops also will stay under control. So that's common sense. So we don't need any formal proof. But be careful. It's the other way around. What if we concluded that sigma An converges? Then we cannot say anything about Bn. If the small guy stays under control, who knows about bigger drops? So then you cannot use inequality that way. So there's always one direction in which you can use it and one direction where you cannot. Now the other way around, if the smaller guy reaches infinity and overflows, then bigger guys, bigger drops will also overflow in common sense. So that's it. We'll see a very similar test, which is limit comparison test. Limit comparison test is slightly less intuitive, but easier to apply. Because for direct comparison, you have to be fairly skillful with inequalities, and that's not always so simple. So here is example number 12. Actually, the big, let me put it down and then we'll talk. Sum n goes 1 to infinity, 1 over 4 cubed of n minus 1. Generally, the biggest skill here is you don't get both sequences. One sequence is given, and the other one you need to come up on your own with your other sequence. Usually that other sequence has to be nice. That means something that you already know, its behavior. and the other things so that you can organize comparison the way it suits your need. Basically, when I look at this problem, before I go into technicalities, I will just tell you, oh, this diverges for sure. Why? Because that -1 should not make a huge difference. So this basically behaves like a power series, so I can use p-test. So this is n to 1/3, that power is too small. That diverges if it's without -1. Well, what with -1, probably it will behave similarly, that 1 cannot make a huge difference. This is very informal thinking, but that's how we always start our reasoning. And then what are we going to do? I will use, as a comparison, I will use sum of 1 or sum of 4 cube root of n. Then what? My question is, so I know that this one diverges. Why? Because p series. P equals 1/3 is less than or equal to 1. You can say, yes, but what is 1/4? 1/4 will be factored out, so doesn't influence convergence or divergence. That's easy to see. So I know that this one diverges. So the only way I can use this test is actually the divergent one, so that will be my AN. And this will be my BN. But it's a question if they are really lined up the way I need them. I would need this to be greater than this. And it happens that it's really true. So we were lucky, so immediately it was there. So I'll say the following. 4 cube root of n minus 1 is less than or equal to 4 cube root of n because I subtracted 1. These are positive numbers, so I can take reciprocals. 1 over 4 cube root of n minus 1 is greater than or equal to 1 over 4 cube of n. And that's it. So now the sentence comes, according to direct comparison test, since sum 1 over 4 cube root of n and goes 1 to infinity is divergent, our series is also divergent. Yes? Maybe we can add more definition by dominating it. Is also divergent. So it was fairly simple. Let me just make you think about something. What if we were not lucky enough? What if this was plus 1? Then I would still work the same way, but I would have little troubles because then this does not work anymore the way I like it. But then what? I would do the following. I would kind of give a little bit. I would adjust this to be 5. Is that correct? Yes, because that extra cube root of n is greater than or equal to 1, so it's obviously true, and basically I would just need to do a little adjustment here, and everything would work the same way, just with 1/5. Here it is. So as I said, so if you need a little adjustment on that, then you need a little skill to adjust your inequality, to stay basically, not to ruin your divergent status of your, I usually like to call this measuring stick, because that's a series whose behavior you know, and then you see how to measure your series against the measuring stick. Alright, so let me show you that better version of the comparison test, where you don't need to use these little skills to really get exactly who's bigger, who's smaller, and all that. So it's much nicer, actually. I recommend this one even much more. So here I have my 13. Again, they must be non-negative. Suppose an greater or equal to 0, bn greater or equal to 0, and a limit an over bn when it goes to infinity is equal to L. So suppose that that limit exists, and that limit L is not 0. So it cannot be negative number because you are dividing positive and negative numbers. So it's either 0, either does not exist, or it's greater than 0, or it's just 0. So if you get a limit L, which is greater than 0, then sum of an, and it goes 1 to infinity, and sum of bn when n equals 1 to L are equiconvergent. Convergent. That's what it is. So, I gave you the idea of the proof. Basically, what? So what would that be? If a limit of an over bn is L, then what do we know? If your limit is greater than 0, then we know the following, that an of bn is greater or equal to 0. But also less than or equal L plus 1. Why? Because if you are approaching the level L, after a while you might get close to L. So after a while you cannot be above L plus 1 for n greater than a certain number, let's say k. And it's always, all the tests are important after a while. And then what do we get? It's very easy, multiply by bn, we get an is less than or equal bn times L plus 1. And then what? See, if some bn converges, then by direct comparison test, L plus 1 times bn also some converges, and by direct comparison test, sum of an also converges. And then what about the other direction? What if sigma bn diverges? Then we have what? The same way, 0, that a and bn, which is greater than 0, if its approaches L, should be greater or equal to L half. If you are approaching L here, then if I put L half here after some k, you must get close. 4 n greater than some k. That k is not the same one, and then we get the same thing, a n greater or equal to L half times bn. Then when you multiply divergent by L half, if L is not 0, then it's also divergent, so an dominates. It's divergent series L half sum, so it diverges as well. So generally that's where actually limit kind of builds in little simpler technology to apply, but the idea is the same one. So here it is. So that's it. Look how much easier it will be to apply. Problem number 20. As I said, these are really the same test. So number 20. Number 20. So analyze convergence, divergence, n goes 1 to infinity. 5n minus 3 over n squared minus 2n plus 5. Again, I always advise you to kind of look at the problem. So don't immediately start calculating, calling tests and everything. Just look at it and see how it reads. So what happens here? So Members are positive, so nothing to worry about that. So they're positive. So the main thing is to estimate the strength of the members, the size of the members. And then the same way as when we calculate horizontal asymptotes or something like that. You know, when n gets big, of course, 5n is much more important than 3, and n squared is much more important than the other. So altogether, these behave like 5n over n squared, which is 5 over n. So it's common sense that actually I should compare with sum of 5 over n when n goes to 1. So how did I, so that's the main skill here, to come up with a measuring stick. And obviously, that sounds like a good choice because I will get a finite limit, because when you disregard the weaker members, this behaves like 5 over n individually. And what, so here it is, I do limit comparison test, the limit when n goes to infinity. Oh, by the way, should I do with 5 over n or 1 over n? Doesn't matter, the same thing if you really want to have someone from the list, maybe with 1 over n, because I don't care if I get 1 or 5. So let's say 1 over n, doesn't matter. So what do I get? I take my members, 5n minus 3 over n squared minus 2n plus 5. I divide by 1 over n. Then we do little fractions. Multiply by reciprocals, so I get 5n minus 3 times n over n squared minus 2n plus 5. What do I get here? It's a limit. When n goes to infinity, 5n squared minus 3n minus 2n plus 5. And basically powers are balanced, so the main thing here is just, you're going to look at the rule if you want, but really there's no need for that. Let's play basic, divide by n squared. So we get 5 minus 3 over n, 1 n squared cancel out. On the bottom we get 1 minus 2 over n plus 5 over n squared. Then what happens? All these guys obviously approach 0 because n is getting big. So this limit is 5. And according to our test, well, let me record what I said, but just so that we know that we checked that an is greater than or equal to 0 all the time. So members are positive, here members are positive, so since I got the finite limit, it doesn't matter how big it is, 5. We'll learn some other tests in one of the future sections where it's important if numbers bigger than 1. No, here just as long as it's finite and not 0, and we got 5, they are actually convergent. And then of course we know behavior, so they are actually convergent. Since we already know sum of 1 over n is divergent. What do we conclude? So our sum 5n minus 3 over n squared minus 2n plus 5 and goes back to infinity is divergent. Here it is. That was very, very simple, as I said. Much simpler than playing with inequalities, which they work in our favor or against us. This is quite basic. Here just a few exercises to play with this idea. So problem number 28. It is sum when n goes 1 to infinity, tan of 1 over n. So, you know, for comparison, it is quite important to know a little bit about the limits and how functions behave. Just let me recall from here, because look what happens. When n gets big, 1 over n gets very small. So this is tan of a very small angle. And then we know famous limit is that limit sine x over x is 1 when x approaches 0. That's one of the most famous limits. This one we just memorize. It's easy to get using L'Hopital rule because it's 0 over 0. So, what about tan x over x? The same thing. Because limit when x goes to 0, tan x over x, you can write it. Since tan is sine over cosine, I write it sine x over x times 1 over cosine x. This is a 1 and this is 1, so limit is 1. So if you have small angle, here's the way to think of that. If x is small, then tan x is very close to x. So value of the tan and the value of the angle are very similar. And generally you can even geometrically see that. You have a circle, and it's tiny angle. I'm going to draw a little bigger so that you see it. So the angle is this length, sine is this length, and tan is this length. So these three lengths are all very, very small, but very close to each other. So then what? Obviously, tan 1 over n behaves very similar. That's 1 over n. So that's why because I can just tell you, let's choose this measuring stick. But how do you know to choose that one? Because, as I said, for small angle, tan of the angle behaves very similar to the angle itself. And then that's it. So what? We know that this one is divergent. Harmonic series. Then we just do the limit. Oh, everybody's positive, so an greater than 0. So I get tan 1 over n over 1 over n. Then so what do I do here? I can just call this limit because 1 over n is small. So if this is small, this limit is 1 from that reasoning that I had here, where x stands for 1 over n. So I do the underlying function, we said. So this should be okay. Or if you don't want to do that substitution, then you analyze the function. I use the L'Hopital rule, although not, I cannot use it on the dotted function. I just need to use the limit when x goes to infinity. Derivative of tan 1 of, this is much more complicated, is what? Secant square of 1 over x, because I'm calling it x in order to be able to differentiate, times negative 1 over x squared over negative 1 over x squared. They cancel each other out. And then 1 over infinity is 0. I mean, 1 over big number is small number. Secant 0 is 1. Here it is. We got the same thing, but I prefer this general reasoning than heavy machinery where you don't see what's happening. Anyway, so what's the conclusion? Since sum of 1 over n is divergent, sum of tan 1 over n is also divergent. While I was busy writing, I just was a little careless with my limit. It should be written correctly. So here is the answer. Right. Here's one more example. Problem number, I think it's 16. Sum of 2 over 3 to the n minus 5 when n goes 1 to infinity. One warning, when n is 1, actually our first number is negative. But I told you that many times, that really doesn't matter. Behavior of the first few numbers never influences convergence. So an greater than or equal 0 for n greater or equal to 2, and that's good enough to apply whatever criterion you want to apply. Again, if you just look at it, this will converge for sure. Why? Because exponential function increases so fast that generally these numbers are getting very small, it will converge for sure. Formally, I'll say the following, I'll forget this minus 5, that's not a big deal. So I'll compare sum of 2 to the 3 and minus 5 when it goes 1 to infinity, and the sum of 2 over 3 to the n. Am I sure that I control this sequence? Of course, because this is geometric series. Because if I pull out 2, sum of 1/3 to the n, and then goes 1 to infinity, be careful, this is not from 0 to n. So this sum, I don't care what the sum is. I'll just say converges, just because the ratio is 1/3 less than 1. And greater than -1. So this one converges. So if I establish that we are equiconvergent, ours will also converge, and that's very easy. Limit when n goes to infinity, 2/3n minus 5/2/3n. When you multiply by a reciprocal, you will get what? 2 times 3 to the n when you flip them, over 3 to the n minus 5 times 2. And then what do? You cancel 2 and 2, you divide by 3 to the n as infinite expression. So you get the 1 over 1 minus 5/3 to the n. 3 to the n over 3 to the n is 1, 3 to the n over 3 to the n is 1, 5/3 to the n is 5/3. Obviously this approach is 0 because 3 to the huge exponent approaches infinity, 5/infinity is 0, this limit is 1. Doesn't matter that it's 1, as long as it's finite, we said they're not 0, then we know that they are equiconvergent. So the answer is converges. Couple of other problems from your homework list. Actually, what we'll do now is more with that idea of telescoping that I kind of didn't assess as very important. But, you know, we'll learn something from next couple of problems. Here's problem number 34, I think. And that is, estimate the convergence of the following: 1 to infinity, 1/n plus 1 minus 1/n plus 2. Is then plus 2, yes, n plus 1 minus 1/n plus 2. Good. What happens here? One very important thing, I mentioned it a few times in our course, but I think I want to illustrate it here. What is one of the things that we should not do, and it's very inviting to misunderstand the rules about properties of limits. So here I see minus, and I know that all these operators behave very nicely with respect to minus, so I might be tempted to actually split and say, all right, let me calculate each of them separately. And that's okay if those two limits do exist. So if one series is sum of two series and both those converge, then you can split the sum and just get each of them individually. But the problem is that these two do not converge. So whenever that happens, you cannot do that. So you only split if both splitting part will converge, because it would give you a wrong conclusion. Because now you cannot manipulate two things that do not exist. And you will see in a moment that the way it was formulated, actually it does exist. How do I know that it does exist? If you build a common denominator, what do we get? Sum n equals 0 to infinity. I get common denominator n plus 1 times n plus 2, and it will be 1. So basically, I'll rush this because I want to show you something else. This obviously behaves the same way as 1/n squared. If you do limit comparison, you will get that it behaves like a hyperharmonic series. We know from the piece test that this converges. So this guy converges the way it was originally if you don't do that bad splitting. But not only so converges. But actually I didn't need that. And actually I can show you a different way from that telescoping idea. So what I did, I actually made it look worse than it was. So I'm not going to even do this. I will be able even to calculate this sum. Why? Let me erase all these things that I don't want to do. Here's what we can do. Let me just, luckily, we can calculate the sum. So let me calculate the sum. I'll call it as capital N to be sum. I think that's how I called it there. Yes. N equals 1 to capital N. Capital N is a stopping value. 1 over n plus 1 minus 1 over n plus 2, which is what? When n is 1, I get 1/2 minus 1/3. Now I will write a little strange so that you see that cascade. When n equals 2, I'll get 1/3 minus 1/4. When n is 3, I'll get plus 1/4 minus 1/5. Dots. And then the last one will be 1 over n minus 1 over n plus 1. And generally, we were able to calculate the sum, take a limit, and everything works perfectly well. Why? Because here's what happens. Those numbers cancel each other out. Then minus, so you always cancel below. So this 1 over n will be canceled with a guy hidden in the dots. So we have only first and the last member. So first member is 1/2, and the last one is n plus 1. And then what? Then, since I was able to describe Sn so nicely, so sum n goes 1 to infinity, 1 over n plus 1 minus 1 over n plus 2 is the limit of S capital N when capital N goes to infinity, which is the limit when n goes to infinity, 1/2 minus 1 over n plus 1. Of course, 1 over huge number approaches 0, so this limit is 1/2. And not only that we concluded that it's convergent, we're actually able to calculate the sum. As again, this is like nice, neat little trick. Nothing, so we learn much less here. However good it looks, this is just a very special situation where they are both linear, have fixed distance. So generally this works. So let me show you a variation of this one. Again, just so that you can address it properly in your homework. I think this is number 36. Similar idea, just a little adjustment. Number 36. Was there, we want the sum when n goes 1 to infinity, 3 over n times n plus 3. So we want to see convergence, to conclude that it's convergent, and actually even nicer to find the sum, which most often we won't be able to do in this chapter. You know, at least toward the end we'll do a little better. So our questions are not to find the sum when they exist, just to estimate if it exists or not. So convergence steps. So what do we do here? We actually rewrite this like partial fraction decomposition, telescoping. This could be written as a 1 over n minus 1 over n plus 3, because they differ by 3. What if it was 5 here? I would pull out 5 terms and build 3. So you want this number to be exactly that difference. And then what? The same thing as before, but just cascade will look a little different. So how much is Sm again? So I want the sum, and it goes 1 to infinity, 1 over n minus 1 over n plus 3. So what would that be? It would be a 1 over 1 minus 1 over 3. Plus, I'm not going to cascade yet, so this is 1 over 2 minus 1 over 4. No, 1 over 5, sorry. And then plus, now I will cascade. So I will go 1 over 3 minus 1 over 6. And plus 1 over 4 minus 1 over 7 plus 1 over 5 minus 1 over 8. Yeah, I don't know how to cascade this to confirm what's happening. Actually, the idea of cascading probably is not too good here, or maybe I didn't think it over too well. So what's next? So 1, 3, 4, 5, 1 over 6 minus 1 over 9, and so on. And what do we get at the end? We get 1 over n minus 1 over n plus 3. So what happens? We actually have cancellation again, but cancellation doesn't happen immediately like a minute ago. So, so here it is. 1 really never gets canceled, so 1 stays. 1/2 also never get canceled, but 1/3 gets canceled. So it's minus 1/3 get canceled 2 steps down the road. And then 1/5 also gets canceled 2 steps down the road. So minus 1/5 will cancel 1/5. And then minus 1/6 would cancel 1/6. What happens with 1 over 4? Oops, did I mess it up here? Yes, I did. Sorry. Now I understand why my cascade didn't work. Because this was not 1/3, this was 1/4. Sorry. So generally 1/3 will survive as well. Nobody cancels 1/3. And then 1/4 will be canceled. So 1/4 with 1/4. Negative 1/5 with 1/5, negative 1/6 with 1/6. So whenever something appears on negative, 1, 2, 3 steps later it appears on positive, and actually each of them will be canceled. Negative 1 over 7 will be canceled. Plus 1 over 7 somewhere here, and so on. So when this cancellation happens, who is the only one that doesn't cancel in the beginning? It will be 1 plus 1/2 plus 1/3, because they don't have anybody 3 steps earlier. But then at the end, also who doesn't get canceled on the minus, so those that do not have anybody 3 steps later are what? 1 over n plus 3 plus 1 over n plus 2 and plus 1 over n plus 1. Because negative 1 over n plus 1 would be canceled with positive 1 over n plus 1, but that's not there, and that's it. So the same way as before. So here is the expression. So now when we take a limit of Sn, when n goes to infinity, what do we get? Because that's what this infinite sum means. This limit will be what? 1 over infinity 0, 1 over infinity 0, so all these 3 approach 0. They're very small, so our limit is 1 plus 1/2 plus 1/3, and that would be what? 3/2 plus 1/3, which would be 11 over 6. So not only that this time we got convergence, we also got the value of the limit. Once again, as I said, I did it, it's in the book, it's in the homework, but really don't take too much out of these telescoping ideas, because they are really designed just for these special cases. So just it's more curiosity than really methodology.